Okay, so this is an introduction to differential equations. So I'm going to dump a bunch of definitions on you, so bear with me. A differential equation is basically an equation involving a function and its derivatives. So you have some function, say y equals f of x. Usually we just write y, but it's really a function. And of course the letters don't matter, so it could be like f of t or something like that. But let's say it's f of x. But the important thing that makes it a differential equation is that this also involves its derivatives. Typically the most common types of differential equations you'll see are first order, so it will just involve the first derivative, but sometimes it involves the second derivative and so on. The order of the differential equation is the highest derivative involved, so if it only involves y prime, I would say it's a first order differential equation. But if it involves y double prime but nothing higher than that, I would say it's a second order, and so on. A solution to a differential equation is just a particular function f of x that satisfies the differential equation, and we'll see an example. Last part of the definition is an initial value problem, which is a differential equation, so it's some equation involving like y and its derivatives, together with some information. And the most common type of information is they'll just tell you a particular function value, like y of a particular number equals another particular number, like y of 2 equals 3 or something like that. This is most common when you have a first order differential equation. If you have a higher order differential equation, then typically an initial value problem is going to include information about higher derivatives, like you might know y prime of a particular number, y double prime of a particular number, and so on. So if you're given that type of information together with a differential equation, that's called an initial value problem. All right. So let's do an example. It's not going to be too long before we start solving differential equations. We're not going to do that today. What we are going to do is verify that something is a solution, but for today, we're basically going to be told what the solution is, and all we're going to do is check that it is. We're not really going to find it. So let's do that. We're going to verify that k times e to the 2x is a solution to the following differential equation, which, by the way, is a first order one. Y prime equals 2y. So this is what I was talking about. Like, this is an example of a differential equation. It's an equation that involves both y and at least its first derivative. And it doesn't go higher than that because this is first order. So what are we doing? We're verifying that this is a solution to this for any constant k. So I just say if y is this, what I want to do is I want to check that this is true. So I'm going to replace this y with this, and let me figure out what to replace y prime with. Well, if y is this, then y prime is, k is a constant, so that just carries right through. I do the derivative of this, and with the chain rule, a 2 comes down. And sure enough, yeah, let me replace everything. This is this, and that's supposed to be 2y. Yeah, these are the same thing. So that's all we're doing, is we're just plugging it in and checking that this actually does equal this when we replace everything. If it doesn't, then you probably made a mistake, or else somebody's messing with you and telling you to verify something as a solution that actually isn't. So let's do part B. We're going to find a solution to the initial value problem, and it's the same differential equation from before, And now we're given one of these pieces of information like we talked about. Y of a particular number equals another particular number. That's like what this looks like in when you're doing a specific example. So the thing is, we already know. The nice thing about this is we already have infinitely many solutions to this differential equation. We just have to find one of them that satisfies the initial value problem. And when I say infinitely many, that's because k could be any constant. So I have the power to choose any value of k I like and hope that I'm able to choose some value that makes this true. So that's what I'm about to do. Write a word here. So if y is this, then, well, y of 1 would be k e to the 2. And what I want that to be is 3e to the 2. So that tells me what value of k to choose. Like I said, we should be able to choose some value of k to make this work. And the way I want to state my answer is as a solution to the initial value problem. So a solution means a particular function y. So y was this, except now we know k is 3. So that's a solution to the initial value problem. Okay. So let's do another example. And for this, I'm going to recall Hooke's law. We talked about Hooke's law before. There's a little subtle difference here. So F is the amount of force exerted by a spring. X is the displacement of the spring with respect to like its natural length. So X is the amount, X is the distance, whether it's longer or shorter, from the spring's natural length. And K is just this thing that we call the spring constant. Every spring has its own constant. If it's a really forceful spring that's very strong, then K is large. If it's a weak spring, then K is small. I believe the first time we talked about Hooke's law, we didn't have a negative sign here because we weren't really paying too much attention to the direction of the force. But let's put a negative sign here. In particular, of course, if X is positive, that means the spring is longer than it wants to be, like longer than its natural length. And of course, if you're stretching a spring longer than its natural length, the force exerted by the spring is inward. It wants to go back towards its natural length. So in other words, when X is positive, the force is pushing it in the opposite direction. And likewise, when X is negative, meaning that the spring is shorter than it wants to be, the spring is pushing it out. So it's the opposite direction. So if I'm paying attention to the direction, then I'm going to put a negative sign here. Okay. So we have some spring, and the natural length doesn't matter too much. I changed my mind and made it 12, but let's say it's 12 meters. And to make our lives easy, let's say that it has a spring constant of 1, and then the units, if you think about it, should be newtons per meter if we're in the metric system. So we have this spring. One end is attached to a wall, so we've got this picture, and the other end is attached to a 1 kilogram block. And yeah, basically we're going to imagine sort of like stretching or maybe compressing the spring a little bit and then letting it go, and it's going to sort of go back and forth. So that's what we're talking about. So if that's what we're talking about, then this X is going to change over time. Like if I squish the spring a little bit and then let it go, then probably it's going to push outward, so x is going to increase, and then it'll go back and x will decrease, and so on. So x of t is the displacement after t seconds. And I'm going to write a differential equation. So this differential equation is derived from Hooke's law. So let me go through this. Force is mass times acceleration. The mass of this block is one kilogram, so that's this one. So yeah, force is mass times acceleration, and the mass is 1. The acceleration, since x is basically our position, of course it's the position relative to the natural length, but so the acceleration is the second derivative of position. So this is mass times acceleration, that's my f. And then that should equal negative k, and we were told that k was 1, times x, so x of t. That's my differential equation. And so this is a second order differential equation if we want to talk about orders, because it goes up to the second derivative and not any higher. And, you know, 1 is just 1, so we can simplify it this way. Often you don't really write of t everywhere, so this is sort of the quicker way of writing it. X double prime equals negative x. Okay. So eventually, or yeah, maybe, I guess not in this class, but if you take differential equations, you will learn how to solve second order differential equations like that. But like I was saying today, we're not really going to solve these things. We're just going to check a solution that's given to us. So we're going to verify that for any constants a and b, we have a solution of this form. Okay, well, I've got some space down here. So, yeah, this is like what we did, except now it's a second order differential equation. So I'm going to say x is a sine t plus b cosine t. And I want to plug it in here. So what I really need is I need the second derivative. So here's the first derivative. And of course, when I write x prime, that's the derivative with respect to t. A cosine t minus b sine t. And then finally, the second derivative is negative a sine t minus b cosine t. So to verify it, we plug in here. So here's x double prime. I just wrote that down. And that's supposed to equal negative x, so here's negative x. And we should actually look at it to verify that it's true. We shouldn't just blindly put a check mark here, but this side better equal this side. Of course, it's really not hard to see because the negative sign distributes. I get negative a sine t, negative b cosine t. Sometimes you might have to do a little bit of algebra to actually check that this side equals this side, but in this case, it's really easy to see. But that's what we're checking. So since we observed that, we put a check mark there. So that's verifying that it's a solution because it worked. Let's do part B. Yeah. So, yeah, so maybe I can be a bit terse about this. So this is like the last one. We already know infinitely many solutions because we know that for any constant a and any constant b, and there's infinitely many choices, we have a solution. All we have to do is find some value of a and b to make this true and make this true. So let's assume that we're going to find a solution of the form that we already know. Let's see. I want x of 0 to be 3. Well, according to this formula, x of 0 would be, okay, I'll go fast with this. Sine of 0 is 0, so this goes away. Cosine of 0 is 1, so x of 0 would just be b. And I want that to come out to 3. Great, we just figured out b. I also want this to be true, right? I just used this piece of information. Now I'm going to use this piece of information. So x prime of 0. So if I'm smart, I can take my answer from here, because I already found x prime, and just plug in 0 to that. So cosine of 0 is 1. Sine of 0 is 0. So we just got a to be negative 2. So our solution is this with this there and this there. So negative 2 sine t plus 3 cosine t. So yeah, I don't know, just a quick word. I think it's cool that sines and cosines show up as a solution to this, because, I mean, basically that means that, you know, the motion of this block, it's like a sine curve or a cosine curve, so it just goes back and forth. So it's, of course, that's not really reasonable in the long run. Like, there's friction, so it's not literally going to go back and forth forever like a sine function. But, you know, if you ignore friction, then it does, I guess.